Hello friends, in today's question, a wooden stick of length L, radius r and density rho has a small metal piece of mass m of negligible volume attached to its one end. Find the minimum value of mass m in terms of the given parameters that would make the stick float vertically in equilibrium in a liquid of density rho, whose density is greater than the density of the metal piece. So in this case, we have to find out that the body, you can say the stick along with the metal piece in equilibrium, and so it means the body or stick should be floating vertically. So which basically means that the net torque on the stick should be equal to 0 and the buoyant force should be able to balance the total weight of the system. Here system means stick, weight of the stick as well as the small metal piece mass. So this entire, you can say, a solution is more or less based on the center of gravity versus the center of buoyancy. So let us start with the basic statement, and we can call that as floating in equilibrium. Floating in equilibrium, and in this case it is given that the stick floats vertically the stick floats vertically, and for it we can say that net torque acting on the stick should be equal to 0. Net torque acting on the stick is 0, and secondly, buoyant force balance the total weight of the system. Buoyant force balances the total weight of the system. Here system means total weight of the system, and system means stick plus small mass m, and secondly it will be with respect to center of gravity versus center of buoyancy. Center of gravity versus center of buoyancy. So based on this, we can write that for rotational equilibrium, the center of mass of the system, which is stick plus small m, should be below the center of buoyancy. So you can say for rotational equilibrium, the center of mass center of mass, that is our COM of system, and here system means stick plus mass m, must be below the center of buoyancy, must be below the center of buoyancy. And we can write this as COB. So the center of mass, that is our COM, it will be the weighted average location of the system mass. Weighted average location of system mass. And our center of buoyancy, it will be equal to midpoint of submerged length. Midpoint of submerged length. So let us draw an approximate diagram for it. Suppose this is a container, the liquid, and we have a stick, something like this, and we assume that the length which is submerged in the liquid is given as h, and the total length is given as L. So midpoint of the submerged length, that is h. Now we are going to find out the total weight of the system. And total weight of the system means weight of the stick plus the mass which is attached somewhere here. So the mass is attached somewhere here. So this is the mass attached, small m. So we can write total weight of the system total weight of the system so the total gravitational downward force, total downward gravitational force will be equal to mass of the stick plus small m multiplied by g. So this is the mass of the stick given as capital M, and the mass of the stick can be represented as capital M is our mass of the stick which will be equal to pi r square L and multiply by rho. and the upward buoyant force let us call that Fp, will be equal to pi r square h submerged part and sigma multiplied by g. And total downward force, let us, that is given as Fw, and the buoyant force is Fp. And in equilibrium, or we can say for vertical equilibrium, Fw should be equal to Fb. We substitute the value, we get this as m plus small m multiplied by g should be equal to pi r square h sigma g. G cancel with g, and from here we can find out that our h will be equal to m plus small m divided by pi r square, and this is sigma. So this is the height of the submerged portion of the stick. Let us call this as equation number 1. Now second, we find out the center of the mass. Center of mass. And center of mass means center of the system, and system means stick plus small m. Center of mass of the system, and system means m plus small m. So we can write that height of the center of mass HCM will be equal to, and we have its basic formula, and that basic formula is our that mass capital M multiplied by the length, that is L by 2, plus small m multiplied by 0 and divided by m plus small m. So we are going to find out the center of mass of the entire system, and for entire system means that the stick having a mass capital M, and we have a small mass m that is connected at the bottom, and this we are taken as a reference point. Okay, so we are going to find out the center of mass of this entire system with respect to this point. Point P. So we can say with respect to P. P means this point where the mass m is connected, small mass m is connected. So we get our height of center of mass will be equal to m multiplied by L by 2 and divided by m plus small m. And we know that our center of mass, or we can say the center of buoyancy, is located at the center of submerged length, that is half of submerged length. So now let us find out center of buoyancy, and center of buoyancy is located at the center of submerged length. Submerged length, and the submerged length is our capital small h. So we can say our center of buoyancy, sorry, will be equal to h upon 2. And for stabilization, the center of mass as well as this center of buoyancy should be equal. So you can say for stabilization, HCM, let me call this HCOM. HCOM should be equal to HCOB. So we substitute the values and we are going to get this as m multiplied by m L by 2 divided by m plus small m is equal to, we have h by 2. So from here we can say that our h will be equal to this 2 cancel with this 2 and we are left with ml divided by m plus small m. So this is also the height of the submerged part. Okay. So let us call this as equation 2, but we already know from equation 1, we already know that our h is equal to m plus small m divided by pi r square sigma. So we can equate these two equations because they are representing same. Therefore we can say that m plus small m divided by pi r square sigma is equal to ml divided by m plus small m, and this can be written as m plus small m whole square is equal to ml by r square sigma, and this can be further written as m plus small m is equal to ml by r square sigma and its square root. And we already know that capital M is given as pi r square L multiplied by rho. So we substitute here in this equation and we can write this as our small m will be equal to, with substituting value, we get this as pi r square L rho multiplied by L pi r square sigma square root, and minus, it will be minus of m, but this will be coming in this side, so minus, and we are going to have minus of m, that is pi r square L upon L multiplied by rho. And this can be easily simplified now. We get m is equal to, we have pi and pi, this will be pi square, and this term will be r4, pi square we can take common, so this comes r square pi, we can take also our L square common, so this will be L out of the square root, and inside the square root will be left only, that will be our rho minus sigma, and we have minus pi r square L multiplied by rho. Now it is a simple manipulation. We can take certain things like pi r square L and pi square common throughout. So we can say this is pi r square L, and we are left with inside at, this will be rho minus sigma, and we left with this as minus of, so missed it, rho. and we can take rho also common. So we get this as pi r square L rho, and this comes as square root of 1 second, I think I missed something here. Yes, this part I missed it. This is sigma multiply product, these two term and this term, this is product, and here also it should be multiplied by sigma. Yeah, I think now it's correct. This comes rho upon sigma minus 1 and its square root. So this is the value of the mass which we are supposed to find out. Now there is another way in which we can calculate it, and for that we can use, you can say the net torque on the stick will be equal to, should be balanced actually. So let us try that approach also. So we have second method. One second. Yes. So here it has to be rho. Now it's correct. I think rho. Okay, let's start with the second method. And for the second method, let us draw the diagram. So this is our liquid surface, and we have stick which is making the angle theta with the level of the liquid, that is horizontal, and there is a mass, small mass here. So the force of this mass will be acting in the downward direction, that will be mg. So let us call this as point A, and the total length of the stick is our L. So capital L is the total length of the stick, and total length of stick, so let us call the center of this entire stick is C. So C is somewhere here. So therefore mg, capital Mg will be acting downward direction, and there will be a buoyant force that will be acting in the upward direction. So that will be because of only the submerged part on the liquid, and the submerged part, let us call that as small l, and this is our point D. So we are going to have upward direction buoyant force. This is point, let us call this as point as B, and this will be the buoyant force in the upward direction. So we start to explain this diagram basically. So we say A is the lowest point on the stick where mass small m is attached. A is the lowest point of the stick where m mass is attached. And we already know that total mass of the stick, that is capital M, you can see the mass of the stick, the mass of stick is given as capital M, and that will be equal to pi r square L multiplied by rho. Okay. And if C is the center of mass of this stick, if C is the center of mass of the stick, if C is the center of mass, sorry, if C is the point, my mistake, if point C represents the center of mass of the stick, then we can say the length AC will be equal to L by 2. Then we can say the AC will be equal to L by 2. Okay, and this we are measuring with respect to point A. And we also say that the length of the rod inside the liquid is small l, that is AD. So we also say that length of stick inside the liquid that is our AD is given as small l. So it means the weight that will be displaced by the stick will be given as, we can say, the weight of the liquid displaced by the stick that will be given as, that is will be equal to our mass mw multiplied by g, and that will equal to pi r square L sigma multiplied by g. And we also can find out the center of mass displaced by for the liquid. Okay, so this will be our center of mass for the displaced liquid where the buoyant force is going to act. Sorry. So therefore we can write that the center of mass of the displaced liquid, the center of mass of the displaced liquid, that is the point B where buoyant force will be acting. Buoyant force will act. Buoyant force will act. So we can call that length will be equal to AB, and AB will be equal to length inside the liquid divided by 2. And this, please remember, everything is calculated with respect to point A. we can say with respect to point A. And we also say, like in the figure, we said that the stick is making an angle of theta with the level of the water, or we can say with the horizontal. The stick makes angle theta with the horizontal. Therefore, now we can find out all the forces which will be acting on this stick. Forces acting on the stick. So first force will be weight, which will equal to mg, and that will be acting downward at point C, because C is the center of mass of the stick. And second will be the weight of attached mass. This is weight of stick. Next is weight of attached mass m, and that will be also equal to mg, acting downward at point A. Next will be the force of buoyancy, which will be acting upward. Buoyant force, which we just said will be equal to our mwg, and this will be acting upward at point B. And for equilibrium, the net force on the stick should be equal to 0. In equilibrium, net force on the stick equal to 0. So based on this, we can write that our mg plus small mg should be equal to mw, that is the buoyant force multiplied by g. And we already calculated this part, so I'm going to just write the result here. So from here we can write, and this will be giving me pi r square multiplied by sigma L minus rho capital L should be equal to m. And also the net torque about the center of mass C should be equal to 0. You can say net torque on the stick about center of mass, that is point C, is 0. So we can write the equation, and the equation will be coming as mg L by 2 cos of theta should be equal to mwg, and the length is our bc cos of theta, which will be coming as pi r square. We have L sigma g, and cos of theta, let me write, equal to pi r square, and we have L g L minus small l divided by 2, and this we have cos of theta. And this is our equation number 1, and this is our equation number 2. So from equation 1 and 2, from equation 1 and 2, we can write that our m square plus 2 pi r square L rho multiplied by m plus pi r square L rho, and this comes as whole square multiplied by 1 minus sigma upon the rho is equal to 0. Now this is a quadratic equation, and obviously it is going to have two solutions. So one of the solution, so we can put it directly, value of m will be coming as pi r square L square root of rho, and this comes as sigma divided by rho minus 1. So in both the cases, the answer will be coming as same. Okay. So only thing we have to keep in mind that the position of the center of mass with respect to the center of buoyancy. Okay. So this completes the question. Thank you.